Good morning, dear students. Today we will discuss regression analysis. In our last presentation, we discussed correlation, which is a part of bivariate statistic, and under that, it is a measure of association, right? When you have to check measure of association between two or more variables, you will be starting with correlation, then you will be further progressing towards regression analysis. So here we are. Bivariate regression basically is a measure of linear association that investigates a straight linear line relationship, and it is useful in forecasting. For example, you have your company's 10-year sales data. You can actually forecast 11th year's sale data as per the previous year's sale, right? So here's the formula. Bivariate linear regression consists of the formula like this: y is equal to a plus bx. It is a measure of linear association that investigates a straight line relationship, right? Y is equal to a plus bx, where y is our dependent variable and x is the independent variable. B is a and b would be calculated. These are basically the constants, or we can say that b is your slope and a is the constant term here, right? When we have some data of companies for 5, 10, 15 years, then we can easily calculate easily forecast for the 16th, 17th, 18th year, right? For that purpose, it is used in most of the business organizations as on today. Let us see what a and b are. A basically is your y-intercept. It is an intercepted segment of a line, and it is a point at which a regression line intercepts the y-axis, right? Where it would be touching the y-axis, that is the point A. B is your slope, the inclination of a regression line as compared to a baseline. With the baseline here is your x-axis, and it is basically rise over run. Let us see it from here. Like in this particular line, where this line would be touching this y-axis, this would be the value of A, and this slope basically is your value of B. Like this, right? And you will be calculating this with the help of delta y divided by delta x. Then you can see least squares regression line as well, like this. In case of dealers, for example, you have got 10 dealers and you want to check how they are associated with the product. Sometimes it is like, every dealer is almost the same. Some are good in some parameters, another one are good in some parameters. So you can just draw a line for them as per their behavior traits and everything like that, and you can know which is the best one, like this, with the help of regression line. This tells you explained and unexplained variation, like this. This is your total deviation. This is your total deviation, but this is the deviation which is being explained by regression equation, and this part, the upper part, is not explained by the equation. So this is how we will be calculating total deviation as well. Total deviation is equal to deviation explained by the regression and plus deviation not explained by the regression equation, right? This is also very important when it comes to regression equations. Why do we use least square method? This is relatively a simple mathematical technique that ensures that the straight line will most closely represent the relationship between x and y. It would try to take care of all the elements, right? And it would tell you in the end that yes, this much of the deviation was explained in the equation, and this much was not explained, right? So that is also important to know how much deviation is explained by the regression, and least squares tell you about that particular deviation as well. It uses the criteria of attempting to make the least amount of the total error in prediction of y from x. It would try to attempt that you will be getting least amount of error while predicting y from x. For example, on x-axis is your advertisement budget and on y-axis is your expected sales, right? How much advertisement should you go with so as to expect this much of the sales? More technically, the procedure used in the least squares method generates a straight line that minimizes the sum of square deviations of the actual values from this predicted regression line. This is how you'll be calculating a regression with the help of least square method. Summation of I is equal to 1 up to n, where n is your number of observation, I is the particular observation we are talking about. I is for first, second, third. I is from 1 to n, and then E in the leg I, E square is minimum. E square minimum, that means you are trying to make the error minimum possible, and it would be calculated by yi minus y cap. And what is this? This is basically called as residual as well in case of regression. Residual or error term. Then yi is your actual value of the dependent variable, and yi hat is your estimated value of the dependent variable, and this would tell you how much error we have. Then logic behind the least square technique is that no straight line can completely represent every dot in the scatter diagram. We have just noticed in the previous ones, like this line cannot present all the dots, right? So that is why we are trying to use least square method. There will be a discrepancy between most of the actual scores and the predicted score. Yes, it happens. If we take, for example, if the line is the predicted score and actual dots are the actual scores, then there is always a discrepancy. There might be very few dots which would be coming on the line. That means on the predicted score. Uses the criteria of attempting to make the least amount of total error in prediction of y from x. This is the beauty of least square technique. And this is your y cap is equal to a plus bx. We have already discussed it, and generally a would be calculated with the help of y minus beta x, right? And here is the example for beta, like it would be n into summation of xy, x into y, minus summation of x into summation of y separately, divided by n into summation of x square minus summation of x the whole square. There is a difference between two values and we might mistake it sometimes. So you have to take care of this. Here it is summation of x square and minus summation of x the whole square. And these are the values for these. Beta basically is the estimated slope for the line. A is your estimated intercept. Y is dependent variable. Y bar is mean of dependent variable. X is independent variable and X bar is the mean for dependent variable, and N is number of observations. These are the values used all over here. Then F test is procedure to determine whether there is more variability explained by the regression or unexplained by the regression. It would tell you how much variability is explained by the regression. So that is why it is very important, and it would be given in the analysis of variance summary table. Whenever you apply regression analysis on any of the values or for anything, then you will get 4 or 5 tables generated, which would be giving you all the details related to analysis. One would tell you which one of the regression analysis you have applied. One would tell you all the regression related values. One would tell you analysis of variance, basically F test. One might tell you that these might be the rejected variables. So many things are there, and this is also one of the very important parameter, F test. Total deviation can be partitioned in two ways. Total variation explained is equal to explained variation plus unexplained variation. And you will be calculating total variation with the help of yi minus y bar. The whole square ka summation, right, is equal to explained variation means yi hat minus y bar, and Unexplained variable would be the actual yi minus yi hat, the whole square, and then summation, right? So there's just little difference between these two, and you can actually calculate the value of explained variation as well as unexplained variation, and it would be equal to your total variation explained, right? And you can even call it as explained variation plus error term, and these both the values would be given in the tables whenever generated through any software. And here is mean of the total group is y bar, then y is the yi is the actual value, and then this yi hat is the value predicted with regression equation. So basically this is that line, we have just checked it in the diagram. That particular line is y hat, mean of the total group is y bar, and I is the actual dot putting in somewhere. So with the help of this we are going to calculate total variation explained. Total variation basically is the actual value minus mean, the whole square ka summation is equal to your estimated value minus mean, that is your explained variation. And when you go with actual value minus estimated value, that would be the unexplained variation. And we can see that this is not explained, this is actually not explained here. The actual value minus the predicted one, that difference is still there, that is not explained anywhere. Then coefficient of determination. This is another variable we'll be looking at while calculating anything with the help of regression analysis. The proportion of variance in y that is explained by x is basically the r square, right? So this would tell us how much variation, how much variance is being explained by the equation generated by regression. This is a measure obtained by squaring the correlation coefficient, that proportion of the total variance of a variable that is accounted for by knowing the value of another variable. Or r square can be calculated as your sum of squares for residuals divided by sum of squares total. Or it might be 1 minus SSE, that means sum of squares for error term divided by sum of squares of total value. After bivariate regression analysis, here comes multiple regression analysis. This is basically the extension of bivariate regression. When we were talking about bivariate regression, we were just talking about two variables at a time, and one among them was dependent variable, another one was independent variable. It was like one variable is affecting the other. For example, your advertisement expense is affecting the sales of the company, right? That is just this is just like two variables are there, one is your advertisement expenses and another one is your sales. But when you say that these two variables are okay, but I want to add here one more variable, that like you might have improved product as per customer's choice, so changes in the product might also affect the sales of the product, or you might have decreased the price of that particular product we are talking about. So you might want to add 2 or 3 parameters more to the regression equation, then it would be like multiple regression. In bivariate regression, we had the equation like y is equal to a plus bx. In case of multiple regression, it would be like y is equal to a, that is your constant term, plus b x1 b1 x1, that is your variable one. For variable one, for example, your advertising budget, then b2 x2, that might be for the pricing, then b3 for b3 into x3, that might be for your improvement in the project, improvement in the product, plus error term, right? So this is how we'll be going with multiple regression. Almost same formulation would be there, but the multiple but because of an increase in number of variables, some complexity would increase. This is multidimensional, where 3 or more variables are involved. almost everything is similar here. Like in case of bivariate regression, we just had one independent variable and one dependent variable. But in case of multiple regression, we would be having one dependent variable and multiple independent variable. And sometimes we have some variables as you can say some variables which might be control groups. For example, age of the company, that also might matter to the sales of the company, right? So that might be, you might introduce that as the control variable, and you'll be putting that particular variable in the end after all the independent variables, so as to check that also along with other independent variables, whether that particular variable is creating any effect on your dependent variable on the sale of the product or not, right? So this might give you more exact value for the more exact reason for the increase in sale. That is why we go with multiple regression, so as to check whether that independent variable is the only reason that your sale is increasing, or there are multiple reasons. And it simultaneously investigates the effect of two or more variables on a single dependent variable. That is the beauty of multiple regression. That's all. Let us see how it is. It can be done with the help of Excel sheet like this. All the simpler analysis can be run with the help of Excel sheet as well. You can use the software SPSS, SAS, Minitab. All the softwares are available and they are very easy to use. They are very user friendly, right? For example, you have the data like this and you will be just going to the formulas and you will be choosing regression, and it would be asking you where to put dependent variable and where to put independent variable. You'll be putting both the variables there, and then you'll be checking correlation and regression, right? For example, you can see here population and retail sales are being correlated, right? And it shows that they are 0.84% correlated. That means 84% correlation is there. That means they are very highly correlated. When you see that these are correlated, highly correlated, you can move further towards regression analysis now. And this is how you will be getting the result for regression analysis. And here you can see your R square value, which is 0.71724. That is quite good. If this value is higher than 0.60, that means it is explaining explaining the analysis well. And then we have discussed an ANOVA table would contain the F value and significance value. This would tell you whether this model is fit or not, and the F value would again tell you the variance explained by the equation. Then you'll see the value here, intercept and population, right? From here also you'll be checking the values, like how much they are affecting each other, right? Then this is the intercept value, basically is the constant value, the value of A, and this value would be the value of B, right? We'll be calculating both the values from here, A and B. If we have more than one variable, as you know, as an independent variable, then we'll be having more variables here and we'll be calculating more values, like value of A, then B1, then B2, then B3, and so on up to Bn. Okay. Then this is how you can generate your graphs also as per correlation, like change in ticket price is shown with the blue line and change in player salary is shown with this pink line, right? Then you can see that these both are increasing. In actual, these two things do not have any correlation with each other. These are totally different things, but still they will show that they are correlated because these two are increasing almost together. And this is how you'll be getting a correlation table for you, like average ticket and player salary is 0.99 correlated. That means these are very highly correlated with each other, right? And their change is also very highly correlated. It's 0.75. That means high correlation is there, right? So this is how you will be getting tables generated with the help of different softwares. This was with the help of Excel sheet. You can do the same analysis with the help of any software available for statistical analysis, that is SPSS, SAS, Minitab. SPSS is most widely used software these days. it takes very less space in your system, and it does the analysis beautifully. It does not require much more things like you do not have to convert data a lot. You can just copy paste it from Excel sheet, and it requires the minimum possible changes. So this is the most friendly statistical package we have. You'll find it very easy if you use it once. And Excel sheet also have all the statistical analysis we have discussed till now. It does not have further analysis, multivariate analysis, but till now it contains all the analysis. That's it. Let us discuss some true false. Number one, in regression analysis, the equation of a straight line is y is equal to a plus bx. Yes, we have done it numerous times till now. So it is, you can remember it. It's easy to remember because we have discussed it again and again so many times. It is true. Second is, in a regression equation, the slope of the line b is the change in x that is due to a corresponding unit of 1 unit of y, corresponding change of 1 unit of y. Is it? In a regression equation, the slope of the line beta is a change in is a change in y that is due to a corresponding change of 1 unit of x. So it is opposite here. So that means it is false. In a simple regression, row parameter estimates reflect the measurements scale range. Is it? In simple regression, row parameter estimates reflects the measurement scale range. Yes, they do. So this is true. Next is, in regression, the standardized y-intercept term is always 0. Sorry, it's always 1. In actual, it is always 0, so it is false. Fifth is, if the purpose of the regression analysis is forecasting, then standardized regression estimates must be used. Is it? It's basically row parameter estimates must be used for forecasting, not the standardized regression estimates. Sixth is, one way to determine the relationship between x and y is to simply visually draw the best fit straight line through the points in the figure. Yes, this is, you'll be, best fit line is always called as simply regression line. So it is true. Seventh is, the ordinary least squares method of regression analysis is based on the logic of how much better a regression line can predict values of y compared to simply using the mean as a prediction. Is it? Yes, this is true. Next is, eighth is, the least squares regression line minimizes the sum of square deviations of the actual values from the predicted values in the regression line. Yes, true. Ninth is, the statistical significance of a regression model is determined by a C-square test. Is it? It is determined by F-test. F-test provides you the statistical significance of a regression model. So it is false. Next is, the coefficient of determination reflects the proportion of variance that can be explained by the regression line. Yes, it is. It is true. Self-assessment questions. Discuss the pros and cons of row regression estimates and standardized regression estimates, and discuss when each one is appropriate. Regression parameter estimates can be presented in either raw or standardized form, right? That is why we are trying to discuss the pros and cons of these two methods. One is raw regression estimates, another one is standardized regression estimates, right? One potential problem with raw parameter estimates is due to the fact that they reflect the measurement scale range, right? However, if the purpose is to purpose of the regression analysis is forecasting, then the raw parameter estimates must be used. This is another way of saying that the researcher's primary interest is prediction. But a standardized regression coefficient provides a common metric allowing regression results to be compared to one another, no matter what the original scale range may be. Right. So standardized regression estimates should be used when the researcher is testing explanatory hypothesis. Right. Is that when the purpose of the research is more explanation than the prediction. But if you are going to actually predict something, then you will be using raw regression estimates. Second is discuss the steps in interpreting a simple regression output. How would you interpret simple regression output? Number one, you will be interpreting the overall significance of the model. That would be done with the help of F value and the against P value, right? You'll be checking the F value, and then in another column, P value is also given. You will be checking that. This would tell you the significance of the model, and it should be, defined before the analysis is run, whether it is 0.05 or 0.01, right? 0.01 is for 99% confidence interval and 0.05 is for 95% confidence interval. So you will be deciding which one to go for, and accordingly you will be picking the value, like whether your analysis is fit or not, right? Whether it is significant or not. Then you will be checking the individual parameter coefficient, right? Individual parameter coefficient is then interpreted like you will be getting the value for intercept, and whether that is significant or not. Against that also P value is given, and then you will be checking the value for the parameter you have chosen, whether it is one variable or more than one variable. You will be checking value for all the variables in the same column where you have taken the value for intercept, and then in the end you will be checking the significance value for all of them. That's it for this. And in our next presentation we'll be discussing non-parametric test for measure of associations. Till now we have discussed in this presentation, and in the last one we have discussed measure of association for parametric test. Now we'll be discussing non-parametric measures for measure of association. That's it. Thank you.